Hey everybody, this is Larry. This is me going over bi-weekly contest 47, Q4, count pairs of nodes. So this one is a weird, hard problem that a handful of people got, at least, an hour in. And it is a way optimization problem. I don't know, and to be honest, I'm not confident that my solution is the intended solution or even the best solution, but it is an idea and it passed the test and it had a couple of optimization. So it became a sort of an optimization problem, and I had two wrong answers. One real wrong answer because I had a premature optimization that was wrong, and then the second one was just timeout that I fixed via optimizing. So hit the like button, hit the subscribe button, join me on Discord, and let me know what you think. You can watch me solve it live during the contest afterwards as well. But the idea here is taking note that obviously n is really big relatively, so you can't do anything n square, but y is, it's bigger, but it's not n square, so that's going to be your choke point. And then the other thing is just that queries is less than 20. So I don't know how that factors in that much, but that's the way that I thought about it. And then so we start the problem by just pre-processing into so there are a couple of things. One, the core component that I thought about was, and I'll try to do this with ASCII art. Let's start from the beginning a little bit. But the idea is that, okay, so, we have degrees of every node. So for example, we have, let's say we have these cases, right? This edge case. And then we just basically reason out the formula a little bit. So we say these edges, so degree of 1 is equal to 1, 2, 3. So 3 degrees of 2 is equal to 1, 2, 3, 4. So degree is 4, and then so then now you can get the number of edges incident with so for the number pair, how many of them has at least to one of the edges, right? Well, that is just equal to degree of 1. Oh, sorry, the number of incident edges is just equal to degrees of 1 plus degrees of 2. This is of 1, 2, minus the number of edges between 1 and 2. So that's basically the formula. You could kind of draw it out why this is the case, because we count for every edge between 1 and 2, we count it both in degrees 1 and degrees 2. So that's basically how we get this formula. And once you have this formula, we can the way that I thought about it was to construct, now. So for you're looking at here, you can look at 1, right? So if so now you can construct if degree if node 1, then you have, then that is just I'm going to write shorthand. So you have this minus e of 1, 2. I'm copy and pasting a second, hang on. So you have these things, right? And then if you look at it here, this will give you a number, let's just say A, B, C, D, I'm lazy, right? So something like that, right? And then here, if you put these numbers on a list, you would have A, B, C, D, and let's just say that they're sorted, and we'll talk about the implementation about it later, right? Let's say now we sorted these, and then now we have to now we have everything we need to calculate how many coming from 1, how many number of incident edges has greater than a query, right? So basically, for example, let's say this looks like 3, 4, 5, 6 or something, or 7. I don't know. It's 7, right? And of course, you know that D1 is common on all the pieces, so you can minus D1 on all the sides or something like that. So so there's some optimization you can do. But let's say you have that, and then now now you just have to search for the query for 2. How many, now we can binary search on this array to be like Okay. And let me just actually rewrite this a little bit, because so now using the actual test cases, this is actually I this is actually just copy and paste from here. So it's 5 4 4. Oh, there's no 5. So yeah, so this is 5 4 4. So so this is just in the list of 4 4 5 after it's sorted, and then you ask yourself, okay, for a query is equal to 2, how many of pairs are for number 1, right? Well, here all 3 of them. So 3 for node 1, and then so forth. I'm a little bit hand wavy here, but that's basically the idea. So that, and then now we repeat for each node. So so that's how we start, right? So now we have a pseudocode for each node. We binary search to get the answer, and if we do this correctly, this, roughly speaking, this might be n log n, right? Yeah. And the reason why this is the case is because for each node is n, and we binary search to get the answer. So that's basically the idea that I had to solve this problem. I know that this is a little bit disjoint, and this is I think, like, conceptually it's not that hard, but it's just about optimization in code, and I'm going to go over that next. But basically, once you have this idea, you should be able to kind of play around with the idea, hopefully, to kind of get the answer. Maybe not, because it took me a couple tries, right? But yeah, so this is basically what you would have, and then now this is how I do it. So I make some optimizations, which I'll go over in a second. So yeah, so here we just pre-process all the edge lists. We count the degrees for each node, and then we just count the number of node edges, number of edges from U to V, and then we just count them in an edge list kind of, or edge adjacency set, if you want to call it that, kind of like a sparse adjacency matrix, if you will. That's basically how we did it. And then here, I'm going to delete some of my debugging code. This is what I call like a delta list. So D list contains before, after for this node. This, what is before, after? Before meaning the degrees impact of a given node. After is equal to the degrees impact of a given node, taken account node U, right? Given node V. So that's basically how I did it. I put it in the list, and this may not make any sense in isolation. So we'll go over to the next step, and you can kind of see my thing, right? So the thing is that the difficulty about this problem is that right now, because we only do math on the nodes that have a common edge with the node U, right? What does that mean? That means that for every node in U, there's some other nodes that have common edges with U, and then there's some other nodes that do not have any common edges with U, right? So here we pre-process these in the edges that have common the nodes that have common edges with U, and their impact. So the thing is that if you have to reconstruct the O of n list every time and then sort it every time, it's going to be too slow. So because that's going to be n, for each n, you have to do an n log n for sorting. That's going to be too slow. So we have to do something faster. And this is kind of tricky. And I don't know if that there's a better way. Maybe we'll go over it later. But basically what I did is I keep a sorted list and of every degrees. And you can do this in a multi-set or a multi-set in different languages, or I don't know. Maybe if you have a suggestion in your language, let me know. But in Python, the way that I do it about is using sorted list, and then I just and then I have this thing where I just, for each query I start with 0, and then I invert the and if you watch me solve this live, which you can watch afterwards, I actually initially got have this for loop, this loop with the queries, well, in the outer loop, but I had to optimize it inner because of the things that we will do later, which you'll see. So basically for here, we have a sorted list all the degrees, and then now we try to figure out for each node, how do we modify the degrees list to answer queries for node U? So that's basically what I do here. And yeah, and basically for, first of all, you remove the current degree because it doesn't make sense to kind of, like the degrees of U, node U is not going to connect to node U, so you don't have to consider it. So we remove that. Yeah, do not consider the pair UU because that doesn't make sense, right? And then here is what we calculated earlier, right? Here, how do I say this? Factor in the degree impact of this node, of these edges, and as we said, the before and after is we remove the before because that's basically the degree that that's the total degree that is in before, and then after is now this takes account the negative C, which is the common edges, right? So this basically be like, hey, for each node, for each delta, we just subtract the common edges from it and then put it back in the sorted list. So now we have the degrees list with respect to U, right? To node U, to be clear, huh? And then we just do it for each query with a binary search. For each query, we sum up the answer to the binary search, and this is, I'm not going to explain this part that much, but now that you have the degrees, an adjacency list of degrees, you basically, take the query that you're looking for, you subtract it by the current degree because, so you have, how does, I think it's something like this. You want so for each query, we want a degrees of U plus degrees of V, minus the common, right? And then of course this part we already did in the array, so this is everything that's in the array. So U plus this sorted list, and of course you can subtract this thing over there, so Q minus degrees of U, and then we have this sorted list, and then we have to count. And yeah, and basically once you found the entry point, you have to count the number of things that are bigger than it, right? So that's where the n minus or this thing is, and just inclusive. So that's why there's a -1. But yeah, let me remove this debugging. And then now after we're done, fix this again. So that's basically the answer. It's really hard for me. I don't know that. I don't know. I don't think. Yeah. But yeah. So basically, hopefully that makes sense. It's kind of tricky. It's kind of hard. I don't know how to tell you how to solve this. But at the end, we do it by 2 because you see that we double counted the answer because we basically have, like, for example, for each pair here, we each pair 1 2. So each pair, for pair 1 2, we also count 2 1, and 1 3 we count 3 1. So we just divide 2 to get it out to kind of fix the double counting, and that's pretty much it. So what you may ask, what is the complexity of this? So note that for each edge we will remove it at most one time from the sorted list and then add it back, I guess. But yeah. So a couple of log n operations for each edge, because if you do the amortization, you can notice that even though this looks really scary, it only shows it for each edge, right? In total, the total number of edges will be the number of operations that are done by these removals, and for each edge, so this is going to be y log n, or v, let's say v for vertex. V is equal to vertex, number of vertices. Y is equal to number of edges, and yeah. So this is going to be y log v time, because that gets dominated by this, and of course we times it by q because that's the number of queries. So q times this stuff. Yeah, and this is log v still, of course. So yeah, so that's the time. In terms of space, we just have all of y space, because for every edge we store something somewhere, and that's going to be your worst case. Technically, I guess it's v plus y in case there's no edges. So yeah, so that's your space complexity. That's all I have. I said a lot of stuff. I don't think that this is very clear, but I think if you are able to kind of manipulate it from here, the tricky part is getting this, and then the second tricky part is kind of come up with an invariant such that you can modify the state and then going back and then just do a binary search. I'm gonna make this a little bit smaller so you can screenshot it and then zoom in or whatever you like. This is gonna be really small. This is a lot of code. Okay, I'm just gonna yeah, okay. And I also finished 63rd or so you can find my code there, though it doesn't have my comment. But this is my code. Take a screenshot, whatever you like. Let me know what you think, and you can watch me solve it live next. What is the two we mean? Okay, so they really could explain this, but so 3 is 5, 2 is 6. Okay. Only 20 queries. That's weird. Okay. Oh, and it could be duplicate edges. That makes it weird. Right, and login for each bit. Yeah. Undirected. That's not right. Hmm. Hmm. 3 plus 1, 2, 3, 4. Why is this not? That's right. Okay. Oh, I see. What's N? That's annoying. What are the other ones? Wow, I don't know how to do this then. I was doing it another way. Did the math wrong a little bit. Okay, let's think about it for a second. Hmm. Hmm. That is tough. Trying to reduce one factor. This may be not fast enough, but That's not right. I'm just messing around too much. Just to be 3 and is 4. Oh, because of the smaller case. Oh no. That's fine. That's just this by 2. Oh no, this is too slow though. Maybe timeout, but work for YOLO, because I don't know how to do it. It's gonna take me a long time to figure out how to do it otherwise. Yeah, well, timeout. Oh, wrong answer. So 4, 5. Why did I do 4? These 2. If something's silly a bit. Okay. So 1, 4, 4 connected 5, 1 connected 3, right? And then what's the 2 means again? So that means that I don't know if I could solve this one, to be honest. Okay, that's correct. And 3. This is correct. It's also correct. 5. I mean, not correct, it's consistent. I think I double count a little bit in a weird way. Because I count 5. I only have 6, why do I have 8? It should only be 1, actually. What am I doing here? So the 4 has 2, that's good. But the 3, this one has 2, which is wrong. Because we're searching for strictly greater than 1. And the 2 things of 2 degrees. Why is that? And one of them it's no, one of them is 3 and one of them is 4. So then the 3 one is not good. Why is it a 2? I messed up. Oh, I messed up because I did this thing. Okay. Still maybe timeout though, but at least this is better. Where's my other print statement? But if it times out, I don't know how to do it. I think about a smarter way of doing it. Yeah. Yeah, so this is fast enough, just not for all of them together. That's the problem with Leetcode in general, is that you have these kind of things where I did the math and it should be alright. It's n log n, but it's a very tight n log n. Well, n being the number of edges, but it's very tight. So that's why it doesn't work. See if I can get inspiration here. How many people have solved it so far? Well, people solved it very quickly. Can I do this in a smarter way? No, it's gonna be, and that's too much. If I try to sort it every time. Can I do it backwards? I have to combine the queries. Can I combine the queries? Much faster, but is that right? No, this is already clearly not well. Oh, I just think I just multiplied by 2, so it should be okay. Come on, be fast enough. It's like 10 times faster, but nice. Yeah, okay. Hey, thanks for watching. Hit the like button, subscribe button, join me on Discord. Let me know how you did this contest and how you did on each of the problems. Yeah, have a good day. Have a great weekend. To good health, to good mental health, and I'll see you next time. Bye bye.